Every year, the world melts down more than 16 million tons of silicon metal, a material without which modern civilization would simply grind to a halt. It makes steel stronger, aluminum lighter, and solar panels possible. But here's something almost nobody knows. To create just 1 ton of this metal, furnaces operate at temperatures exceeding 5,400 degrees Fahrenheit and consume as much electricity as hundreds of American households use in a month. So why does this silent giant hide a diamond structure inside? And what discovery about silicon will change your understanding of technology if you stick around till the end? Industries use metallurgical-grade silicon as a foundational material for creating ferroalloys, particularly ferrosilicon, which gets added to steel to improve its strength, corrosion resistance, and ability to withstand high temperatures. How steel deforms, its elasticity, and behavior under load largely depend on how silicon dissolved in the metal matrix behaves. Metallurgical silicon is also critical for producing aluminum alloys, where it's responsible for reducing weight and improving the alloy's ability to maintain its shape when heated. For example, in cast aluminum parts for automobiles, the silicon content can reach anywhere from 12 to 14% by weight. Another key application is obtaining purer silicon suitable for electronics and photovoltaics. Metallurgical-grade silicon serves as the starting point for producing polysilicon, which gets purified to impurity levels in the parts per billion range. This ultra-pure material is what they use to form ingots and wafers for microchips and solar panels. Demand in this sector has shot up dramatically in the US over recent decades, driven by renewable energy expansion and the needs of data centers. To put the scale in perspective, manufacturing a single solar panel module that's about 11 square feet requires roughly 6 or 7 pounds of silicon in the form of high-purity polycrystalline material. Metallurgical-grade silicon has additional applications too. It's used in chemical manufacturing to synthesize silicones, which are needed for sealants, lubricants, medical devices, household products, and electrical insulation components. It serves as the starting material for silanes, compounds that act as coupling agents between organic and inorganic materials, ensuring stronger surface bonding in composites. Certain types of silanes are used as part of adhesives and coatings that help extend the service life of structures in humid or corrosive environments. Technological progress constantly raises the bar for metallurgical-grade silicon, since purity, grain size, and consistency of properties directly impact the quality of the final product. In American industry, research continues on optimizing electric arc furnaces to cut energy consumption, as well as on utilizing carbon monoxide byproducts. On top of that, companies are developing ways to recycle silicon production waste to bring part of the material back into the cycle and reduce emissions tied to mining fresh quartz. All of this makes metallurgical-grade silicon one of the foundational industrial materials. Without it, modern electronics, transportation, and energy sectors couldn't keep up their current pace of development. To turn mineral oxide into metal, you need extremely high temperatures and a carefully controlled reduction reaction. This is done in large electric arc furnaces that operate at massive temperatures and consume enormous amounts of electricity. The furnace is loaded with crushed quartz along with carbon-based reducing agents. Most commonly, these are charcoal, coke, or various carbon briquettes, selected to ensure stable combustion and the right reactivity. Powerful graphite electrodes create an arc that heats the center of the furnace to approximately 5,430 degrees Fahrenheit. Under these conditions, ordinary rocks transform into active participants in the reaction. Silicon dioxide reacts with carbon, and as a result, oxygen is removed from the oxide. Gaseous carbon monoxide forms, while pure silicon transitions into a liquid state. The molten material is heavier than the surrounding charge, so it slowly settles to the bottom of the furnace, accumulating as a metallic mass. Once enough silicon is collected, it's released into special crucibles or troughs. As it cools down, the liquid metal solidifies into solid ingots, which are then crushed into smaller pieces that are easier to transport and process further. At this stage, it's crucial to maintain conditions that prevent impurities from oxidizing again or mixing with the cooled silicon. The raw material obtained at this point already has commercial purity of around 99%. This level of purity works fine for ferroalloys, but it's not enough for more demanding applications. Next comes the stage of refining the metal to higher purity. Silicon can be remelted in a vacuum or under an inert atmosphere, using various methods like sorption, zone melting, or chemical purification. The main goal here is to get rid of impurities like iron, aluminum, calcium, and sometimes phosphorus and boron. The impurity content is controlled with precision down to parts per million, because even a tiny amount of foreign elements can seriously affect the electrical properties of the final product. After purification, you get metallic silicon with the characteristics needed to produce alloys, silicones, or even purer polysilicon. The production process itself is energy intensive, so it's critical that the method ensures minimal heat loss and makes the most efficient use of electrical power. Modern furnaces come equipped with heat recovery systems and electrode feed control. This helps cut down overall energy consumption and boost productivity. Process optimization is a big deal here, because on average, making 1 ton of metallic silicon requires about as much electricity as several hundred American households use in a month. The quality of quartz sand plays a crucial role too. The purer the initial silicon dioxide, the fewer purification stages are needed after melting. Quartz with high impurity content can lead to increased energy consumption and greater furnace wear. That's why deposits supplying raw materials for the silicon industry must meet strict standards for chemical purity and mechanical uniformity of the material. Silicon, though it doesn't have gold's shine, is a true geochemical giant, an absolutely irreplaceable element. In terms of abundance in Earth's crust, it holds an honorable second place, losing only to a non-metal, oxygen. This means that, essentially, we live on a massive silicon-oxygen planet. It's hard to wrap your head around this, but this substance makes up a colossal 27.6% of our planetary crust's mass. Just imagine, almost every 4th ton of material we see beneath our feet is silicon or its compounds. It forms the backbone of entire mountain ranges and serves as the building material for countless minerals called silicates. This element isn't just filler, it's the foundation of our entire modern civilization. As a semiconductor, it powers every chip, processor, and transistor inside your phone, computer, and car. Silicon is the gray eminence of our planet and our technological age. Quiet, abundant, but absolutely omnipotent. Its extraordinary purity is essential for microelectronics, making it one of the most demanding materials in the world. If you pick up any rock or handful of sand, you're holding an entire silicon factory. We all live on a massive silicon planet, not just a water one. Silicon could have been super expensive and sparkly, but it chose the humble path of being a semiconductor to run all the world's electronics instead. Why am I saying this? Because pure silicon has the exact same crystal structure as diamond. To put it simply, why silicon with the same structure as diamond isn't actually a diamond comes down to 2 key differences: atom size and bond strength. Diamond is made of carbon atoms, while silicon is made of silicon atoms. Plus, a carbon atom is tiny, whereas a silicon atom is much bigger. Even though both elements form the same spatial lattice, silicon atoms, being larger, force the whole structure to expand. This makes the bonds between them longer and, as a result, weaker. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. a mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened, and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block, massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious: cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen. a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents. A modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it, a giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about a quarter pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide a resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation: drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Jizan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here, it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian Tunnels. Toronto TTC North Subway Extension, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing, but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities, and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dies. For packaging and bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior US states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on US roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The US continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National Sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash, you have to divide it into 4, sometimes 5 different categories: wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle, that's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself, to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems. educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom.